Good morning. All right. So we're going to pick up where we left off in section 2.3, try to finish that up today, maybe even get into 2.4, and then I'll adjust the homework as necessary based off how far we get. But just know, continue to work on the 2.1 to 2.4 homework. Let me know as you have questions on that. I did get the test graded over the weekend, so you can see your grades and your feedback. If you look at those, all you really have to do is just click on your submission, and you can see all of my comments, including how many points you lost on each problem and then what the correct answer should have been. But if you have any questions about how I graded it, or any questions about how to do the problems, definitely email me or come see me during student hours. I'll be happy to discuss any of that with you. Okay. Any questions, comments, concerns before we get started today? All right, so let's take a look here at example 4. So it says we want to solve the given equation or inequality graphically. Now, the way we're going to do this, for my purposes, because the book does it 2 different ways, I'm always going to use the one way because it always works and there's no reason to learn 2 different methods in this case. Okay, so first step here, I'm going to move everything to one side of this equation, which means I'm going to subtract 2x squared and I'm going to subtract 5x. And so I'm going to do the same thing on the other side now, subtract the 2x squared and subtract the 5x. All right, now if you notice here, there are no like terms on the left-hand side, so I can't combine any of those things. So now we're just left with x cubed minus 2x squared minus 5x plus 6 equals 0. And the order of those terms really doesn't matter at all, right? So I tried to keep them in order from highest exponent to lowest exponent. Now, once we get everything to one side, we want to solve this thing graphically, which means I'm actually going to graph the equation that I've got there now. I'm only looking at the left-hand side of this, though. So what I'm going to graph is y equals x cubed minus 2x squared minus 5x plus 6. So that's the whole reason for moving everything to one side, is so that then I can take the left-hand side, make it an equation, and then actually graph it. And so I'm going to switch over to Desmos now. I'm going to graph that equation. There we go. All right, so now I'm going to put in y equals x cubed minus 2x squared minus 5x and plus 6. Now, if you remember, we set this thing equal to 0. So now what I'm looking for are the zeros of this function. Well, what's another name for zeros of our function? It's the x-intercepts, right? Okay, and it would be the solutions, right? So all those things are equivalent. Remember, there was those 4 equivalent statements, right? That x-intercepts are the same things as zeros, which give us our factors, right? Which are basically wherever the solutions are to that equation where it's equal to 0. Now, if we look at this, okay, that means I'm just looking for all the places where it crosses the x-axis. Well, in Desmos, those are pretty easy to find. We can just click on the points. So we have one here, we have one here, and we have one right here. Now, in this case, because our original equation was just in terms of x, right? That's all I care about, is what are the x value where this thing is equal to 0. So for this one, I have -2, I have +1, and I have +3. Those are going to be my 3 solutions. So we would just have x equals -2, 1, and 3. So in addition to the ways that we've solved, quadratics and things like that in the past, Okay, now you can actually look at a graph and kind of check your answers, right? And there will be some where it doesn't factor very nicely, right? Quadratic formula doesn't necessarily work, and so you might actually want to use your graph to find some approximations of your solutions in a lot of cases. Okay, so always set it equal to 0 first, sketch the graph, and then just look for those x-intercepts, which would be the solutions to your equation now. Any questions on that? All right, so let's go back to the notes. Right, now the second one here, notice it's very similar to the first one, except now we have this greater than or equal to. Now, first step, same thing, I'm going to move everything to one side, which is going to give me x cubed minus 2x squared minus 5x plus 6. This time, though, greater than or equal to 0. Now, at that point, once I've moved everything to one side, I'm still going to graph, right? So I'm still going to graph that same function that we just looked at, but this time I'm thinking about where this thing is greater than or equal to 0. So where would I be looking on my graph to find where this is greater than or equal to 0? Okay, so that would be in terms of x values, right? If the x values were greater than or equal to 0, it would be on the right-hand side. In this case, though, I'm setting the entire function, which is the f of x or the y, greater than or equal to 0. So where would those y values be greater than or equal to 0? So first quadrant is one place, right? But where else? Second quadrant, right? So anything above the x-axis now is going to be where the y values are positive. That's what I'm looking for, is what parts of my graph are now above the x-axis. So I'm going to go back to Desmos. Okay. And so again, it's the same function we just looked at, but now I want to know, where are the values greater than 0? Where are they above the x-axis? Now, we're going to have to use intervals for this because there's multiple places where we actually have values that are greater than 0. So what would one of those intervals be where we have values that are greater than 0? I'll put my x-intercepts back on here. Good. Everything between -2 and +1 is above the x-axis. So we're going to have an interval from -2 to 1. Now the question is, this was greater than or equal to 0. So are we including the -2 and the 1 or not? We would be, right? And so in this case, we would want to use brackets on the -2 and the 1. So we have bracket -2 to 1 with a bracket. All right. And it looks like Greer's got the other one here. So everywhere past 3, right, from 3 to positive infinity is also going to be above the x-axis. So we're going to have another interval now that goes from 3 to infinity. And then the same question, are we including 3 this time? Yes, right? So we need a bracket on the 3. And remember, infinities always get parentheses. Okay, so now we have those two intervals from -2 to 1, from 3 to infinity. That's where our graph is going to be greater than or equal to 0. Everything else on our graph now is below the x-axis. Those intervals are not going to be included in our solution. Again, steps are the same. Move everything to one side, graph that function. But if it's in an inequality, you just want to compare it to 0 now. If it's greater than or equal to, we're looking for everything above the x-axis. If it's less than or equal to, then you're looking for everything below, right? And then if it doesn't have the equal to, you just would not include the values on the x-axis. That's all. Go back to my notes so you can see what I wrote there. All right, so there's my solution from -2 to 1. Again, brackets on both because both of those points are included. And then from 3 to infinity, also including the 3 because 3 is equal to 0 there. Any questions about that one? All right. Increasing and decreasing. Okay, so f is going to be increasing on some interval I if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2. Now, let's just look at the graph, right? So the first graph here gives us an example of that. We have this f of x sub 1 less than this f of x sub 2, where x sub 1 is less than x sub 2. That's what this is saying. In other words, if you look at your graph, it's going up from left to right. Okay, that's all it really means to be increasing. So as long as you can look at the graph and recognize, yeah, I'm always reading from left to right, and from left to right, that is going up. That means we have an increasing interval. Now the second one, the only thing that's changed is now my first f of x sub 1 is greater than f of x sub 2. So this value here is higher than this value here, where x sub 1 is still less than x sub 2. But again, as long as you can just look at the graph and go, yep, reading from left to right, that graph is going down. That means we have a decreasing interval along x sub 1 to x sub 2 now. Any questions about how to look at a graph and determine increasing or decreasing? Again, just always make sure you're always reading from left to right when you're looking for increasing, decreasing. All right, let's get that one. So let's take a look here. We want to sketch the graph of this function. We're going to find the domain and range, and then we're going to list the intervals where it's increasing and decreasing. Okay, so the first thing is we're just going to put it in Desmos, look at the graph. We're going to think about what the domain and range are, and then we'll look at intervals of increase and decrease. So I'm going to switch over to Desmos. Right. So our function this time, we had f of x is equal to 12x squared. It's 4x cubed minus 3x to the fourth. Now, you might notice here that it looks like we're missing part of our graph, right? So the first thing we're going to want to do, since we're looking for domain and range, and we're looking for the intervals where it's increasing, decreasing, we need to be able to see the whole thing. So what would I need to adjust in this case to be able to see my entire graph? The y values, good, right? So I'm going to adjust my y. In this case, it doesn't look like there's anything below, right? If you want to go lower just to make sure it doesn't turn around down there, that's fine. But you can see we definitely are missing something up at the top. So I'm going to go ahead and adjust that. What would you like to make that y value at the top, maybe to be able to see it this time? All right, so let's try 10, see if that works. I'm going to adjust my y maximum value here to 10. And we can see in that case, we're still kind of missing the top part, right? So we still need to even higher. All right, 50. All right, so let's go ahead and bump it up to 50. There we go, right? We can definitely see the top of it if we go to 50. Right, 40 would have been sufficient, but you got to go beyond 30 for sure in this case. Now, again, if you wanted to check just to make sure, right, I'm just going to bump this down to -50. Okay, but in this case, you can see, right, it never turns around again down there. So that is the entire graph that we care about. All right, now let's start with domain and range. Okay, so looking at this graph now, domain is the x values. What would our domain be for this function? Negative infinity to positive infinity, right? There's no restrictions on that function. It's a polynomial, no fractions with x's in the denominator, no square roots. This thing's going to go from negative infinity to positive infinity. Okay, that takes care of domain. Now let's think about the range. Okay, so looking at our graph now, I want to think about the possible y values. What would our range be for this graph? And you can approximate it right now if you want to, and then we'll make sure we have it exact. Okay, so it's negative infinity to 30 something, right? Okay, so negative infinity up to whatever that top point is. Okay, so what I'm going to do, we can actually click on that point in Desmos and see that that exact value now is 32. So it's actually going to go from negative infinity to 32. Are we including 32 or not? Yes, right? 32 is an actual y value on the graph now. So we need to use a bracket to include the 32 in our range. Okay, but our graph never goes above that. Okay, so we never want our range to go above 32. Any questions about finding domain and range from the graph now? And again, I'll go back and show you my notes where I actually wrote out the domain and range, so if you need to see it written out. Okay, but I want to go ahead and get the increase and decrease intervals now based off of our graph. So what are we going to need to know to figure out where this thing is increasing and decreasing? Okay, so where it goes from 0 to a positive, kind of, okay, but again, all we really care about is whether the graph reading from left to right is going up or down, right? And so if we look here, the first, starting as far left as we can in this case, is that first interval going to be increasing or decreasing if we read from left to right? It's increasing, right? If you look at your graph, right, everything from the left-hand side, when we start out here, we are increasing. I'll kind of try to trace that so you can see it. All right, so increasing, increasing, increasing along this interval. Now the question is, where does it stop increasing? Okay, it looks like -1, right? So if we look here, it's this point right up here. That's where it actually stops its increase, right? It doesn't increase beyond that point now. And so what we would say is that this thing is increasing. We always use x values for our increasing and decreasing intervals. So negative infinity to -1. So everything from negative infinity to -1 is an increasing interval now. Now, once we get to -1, again, continuing to read from left to right, what's going to happen? It decreases, right? And so what would be the interval now where it's decreasing? Good. From -1 to 0. Okay, because notice here, when we get to 0, it turns around again. So now we would say we are decreasing from -1 to 0. All right. Now, once we get to 0, what happens? Increases again, right? And so what would that interval be of increase? From 0 to 2. Good. Always using the x values. So we're going from 0 to 2. It's increasing. And then once we get to 2, it turns around again, starts decreasing. So what would our interval be for decreasing at that point? 2 to positive infinity. Good. Because again, we're looking in terms of the x values, right? So x values are going towards positive infinity as we move to the right. So it's from 2 to positive infinity is also a decreasing interval now. Okay. So now that's a good question, Destry. When I write my increasing and decreasing intervals, I always use just parentheses because technically at -1, 0, and 2, it's not increasing or decreasing, right? So those values really shouldn't be included in either one. So I always just use parentheses for these. Okay. Now, some textbooks for some reason use brackets on everything, and they say, well, no, the -1's included in the increasing and the decreasing interval, right? So it's just personal preference, honestly. I won't take off points if you use brackets, but I always use parentheses for these intervals. Okay. All right. Any questions on finding those increasing and decreasing intervals now looking at the graph? Now, one common misconception, right, is a lot of people want to find the x-intercepts and use those for your intervals for increase and decrease. Notice here what we found are all the turning points, right? So I found the -1, 5, that's where it turns. 0, 0, it turns, and at 232, it turns, right? Those are the points we care about when we're talking about increase, decrease now, not the x-intercepts. Right, so I'm going to go back to the notes so you can see what I've got there. All right, so there we go. So our domain again was from -infinity to +infinity, no restrictions on the x values. Our range only went from -infinity up to 32, but 32 was included, so we use a bracket. And then for increasing and decreasing, we had two intervals of increase from -infinity to -1, and also from 0 to 2. And then we had a decreasing interval from -1 to 0, and then also from 2 to infinity. And if you put commas between those, that's fine, or you can use the union symbol. Again, either way, I will take it as long as you got all the increasing intervals and all the decreasing intervals. Any questions on that one now? Again, on a problem like this, I would expect you to use either Desmos or your graphing calculator. If you've got questions about how to find those turning points in your graphing calculator, feel free to ask me, right? And I can send you, I've got some links that explain how to do steps in the calculator and that kind of thing. You just let me know which model you have, and I can send you the directions for how to find those turning points. All right. We're not going to do that one. Okay, local mins and maxes. Okay, so I know this is kind of small here, right? Hopefully, if you've got the slides downloaded, you can see it a little better. So a function value f of a is what we call a local maximum value if f of a is greater than or equal to f of x, where x is near a, right? So again, the picture is better to explain it. But basically, this point up here now is going to be what we call a local maximum because it's the highest y value of all the y values near that x value. Okay? So basically, it's a turning point of your graph now. Now, if we have a local minimum value, it means it's the smallest y value of all the y values that are near that x value. And so notice down here now, we have another turning point. That's what we would call a local minimum. And then we have other examples here of local max and local mins. Notice they don't have to be the absolute highest or lowest points on your graph, right? They just need to be turning points of the graph to be maxes and mins. Okay, but if it goes from increasing to decreasing, we have a maximum. If it goes from decreasing to increasing, then we have a local minimum instead. Right? And if you assume in this case that this graph continues forever and ever, the absolute max and min would be positive infinity and negative infinity. Right? So we're only looking at all those turning points to find local min and max values. Any questions about locating local min and max values from a graph now? Okay. All right, so we want to find the local max and min values of the function x cubed minus 8x plus 1 it says we're going to round that to 3 decimal places. Now, as soon as you see rounded to 3 decimal places, that tells you automatically we're going to use Desmos or a graphing calculator, right? Because we're not going to be able to do this by hand. So first thing I'm going to do, I'm going to go over to Desmos. I'm going to put this function in there, and we're going to look for those local min and max values. All right, so our function this time, we've got y equals x cubed minus 8x plus 1. Now, we had already adjusted our window, and it looks like in this case, the window we've got here works perfectly fine. We can actually see the entire graph. So if I'm looking just kind of from left to right as I go along, am I going to hit a local max or min first? It's a local maximum. Good. All right, so that first turning point that we hit up here, that's what we would consider a local maximum. And it said we were going to round this to 3 decimal places. So what would our local max be? Good. And so negative 1.633 and then 9.709. That's our local max. Now, if it says value, then it only wants the y value, not the entire point. Okay, so just pay attention to that. Sometimes it's going to ask for the local max. It wants the entire ordered pair. Other times it might ask for the local maximum value. In that case, it just wants the y value. So if we're looking at a max value this time, then we would only list the 9.709. Okay. All right. Now, if we continue on, right, from left to right, what are we going to hit next? Now we have a local minimum, right? And so that's going to be this point right down here. Notice the values are very similar, right? We have a positive 1.633 this time. And then our y value is a negative 7.709. Again, we would call that a local min. And again, if they only wanted the minimum value, then we would just use the y value. So our minimum value this time would be negative 7.709. And then looking at that graph, there are no other turning points, right? So, the first interval is increasing up to that first maximum that we hit, then it decreases to the minimum, and then it increases again and continues to increase all the way to infinity. Okay, so those are our only local min and max values this time. So I'll switch back so you can see what I wrote there. And so again, if it just says local max or local min, then we would list out the entire ordered pair. But in this case, it does just say values. So they really just want the max and min value, the y values this time. So our max value will be 9.709, and the minimum value will be negative 7.709. And in the homework, that's one of the most common questions I get is people putting the entire ordered pair in there and it asks for a value and it only wants the y. So just kind of read carefully and make sure you're only giving it the information that it wants there. Any questions on that one now? All right. So that's all we're doing in that section. And again, if you go back and look in the course content folder, I do work out a few more of the examples from this section in that video. So if you ever need more examples, feel free to jump back in there and look at that video. Okay. Let's look at 2.4 now. All right, average rate of change. All right, so what we're going to be looking at now is as you go on an interval from one x value to another, looking at how rapidly the y values are changing, right? That's kind of what we're thinking about now. That's going to give us our average rate of change. Right, now to calculate that, okay, we've got our average rate of change, is just the change in y over the change in x. It's going to be f of b minus f of a divided by b minus a. Now, what does that formula look like? Think about things we've looked at in the past. Does that look like anything we've seen before? It's slope, right? So average rate of change now, we're just looking at the slope between any 2 points. Now, in terms of a function, this is what we call a secant line. So basically, if I have 2 points on my graph and I draw a line through those 2 points now, that's what we call a secant line. And so our average rate of change is the slope of that secant line between those 2 points on our curve. Okay. And again, that terminology, secant line, will come into play if you do go on to take calculus down the road. Okay, but for right now, just keep in mind we're just finding a slope between those 2 points. All right, so now we're given a function x minus 3 squared. Okay, and they give you the picture in the book. I didn't copy it here, but we want to find net change and average rate of change between these points. So we got to think back, because we did net change before. Does anybody remember how we find the net change of a function? Okay, almost, right? Just make sure you start with f of b, right? We always start with the larger x value. So it's going to be f of b minus f of a. So that's our net change formula. So if we look at this one now, what's our a value and what's our b value? What's a going to be? The 1, good, right? So our smaller x value is the a value, which means the larger x value has to be the b. So 3 is going to be our b value. So for net change, we're just doing f of 3 minus f of 1. Now it's just a matter of substituting that into our function and evaluating each piece of that. We're going to start here with 3 minus 3 squared. It's going to give us f of 3 minus 1 minus 3 squared. That's our f of 1. And if we simplify that now, what's 3 minus 3 squared going to give us? It's just 0, right? So 3 minus 3 is 0. 0 squared is 0. So we have 0 minus, and then what's 1 minus 3 squared going to give us? 4, right? Because 1 minus 3 is negative 2. When we square that, it becomes a positive, so we have a 4. And now when we subtract 0 minus 4, that's going to give us what? Negative 4. Perfect. So now we know our net change along that interval is going to be negative 4. All right. Now we need to find the average rate of change. Okay, so that's the formula we just saw on the last slide. It's going to be f of b minus f of a divided by b minus a. Now, if you notice, f of b minus f of a in the numerator is just the net change, right? We've already calculated that. So we don't have to do it all over again. We can just use the value that we just found. So my f of b minus f of a in the numerator, just negative 4. And then what's b minus a going to be? Good, right? Just 3 minus 1, so that's going to give us 2. So now we really just have negative 4 divided by 2. which gives us what? -2. Perfect. There's our average rate of change. And again, it's the slope of that secant line that goes between those 2 points on our curve. Now, what this tells us is because we end up with a negative average rate of change, we know that this function is actually decreasing. It's going down from left to right as we go from 1 to 3 on our graph, okay, because we have a negative slope between those 2 points. Any questions about calculating net change or average rate of change now? All right, let's do the same thing for part B here. So net change, same formula. So what's my A value this time? Good. And the B value then would have to be the 7. So our formula says we're starting with f of 7 minus f of 4. So again, we're going to substitute those values in. 7 minus 3 squared minus 4 minus 3 squared. And if we simplify 7 minus 3 squared, what do we get? Good. 4 squared is 16 minus, and then 4 minus 3 squared would give us what? Good. 1 squared is just 1. And subtracting those now, 15 is going to be our net change. And then again, we're going to do our average rate of change formula now. Now again, I've already calculated the numerator because that's the f of b minus f of a, so that's going to be 15. And we're going to divide that by what this time? Good. 7 minus 4 is just going to give us 3. So when we do that, 15 divided by 3 should give us what? 5. Perfect. So that is our average rate of change between 4 and 7 this time. Any questions on that one? Okay. So let's take a look now. We have a contextual problem. So an object is dropped from a high cliff or a tall building. The distance that has fallen after t seconds is given by the function d of t equals 16t squared. We want to find the average speed, which is just average rate of change, over the following intervals. So whenever you're given a distance function now and you're looking for speed, you can actually just calculate the slope because that would just be the rate of change of your distance, and that's going to give you your speed. So same formula we just used, right? I'm going to let A be the 1, which means 5 is your B value. Looking at f of 5 minus f of 1 divided by 5 minus 1. Now we just need to substitute those values into our function. So this is going to be 16 times 5 squared minus 16 times 1 squared all over, and I can go ahead and subtract here. 5 minus 1 should give us 4. now it's just a matter of simplifying what we have in the numerator. So what's 16 times 5 squared going to be? Should be 400, good. Minus, what's 16 times 1 squared? Just 16. Now if we subtract that, 400 minus 16 should be 384. And if we divide that by 4, what do we get? 96. Good. Now, the only thing else that we need to think about here is because we have a context to the problem, we need to think about units. So we just found the average speed between 1 second and 5 seconds of this falling object. What are the units going to be for that average speed? And I guess it didn't really do a good job of telling you what the units are here. What are the units of time going to be? Let's start with that. Seconds. Now, in this case, the formula that's given, this is going to be a distance measured in feet. Okay, so if that's measured in feet and we know our time is measured in seconds, what is our speed going to be measured in? Feet per second. Good. So this is 96 feet per second. If you think about it, right, the numerator of this, we're using the distance formula to find the numerator. That's our distance. We know the denominator, we're subtracting numbers of seconds, so that's seconds in the denominator, and that's why our speed here is measured in feet over seconds, feet per second. Any questions on calculating that one? All right, now part B. This time t equals a, and our second t value is going to be a plus h. So what are we going to start with for our formula for average rate of change then? Okay, so the net change here, right? We need to think about our A and B values. So what's our A value going to be for this one? Good. And then the B value then has to be the A plus H. So when I start then, if I'm using that net change in the numerator, we're going to have F of A plus H minus F of A. And then what are we going to have in our denominator? Good. A plus H minus A. Again, that's just B minus A. B value is A plus H. A value is just A this time. Right, now we need to substitute. So if I do F of A plus H, what's that going to look like? Good, right? So we're substituting A plus H into our functions. We'll have 16 times A plus H squared minus, and then for F of A, same thing. We're just substituting A into our function. So that's going to give us 16 times A squared. Now, if I simplify the denominator this time, what's going to be left in the denominator? Just the H, right? Because the A minus A is going to cancel out. So we're just left with an H. Now we need to simplify the numerator. So what am I going to need to do first to simplify that numerator? Okay, before we can distribute the 16, what do we have to do first according to order of operations? We have to square it, right? So we have to square the a plus h first, and then we can distribute the 16. Well, a plus h squared, remember, is just a plus h times a plus h. So what's that going to give us if we multiply that out now? Good. A squared plus 2ah plus h squared, right? Because our outer and inner terms would both be an ah term, and then when we combine those, we get 2ah. So we have 16 times a squared plus 2ah plus h squared minus 16a squared all over h. Now we can distribute, right? So if I distribute that now, come down here so we have room. We have 16a squared plus 32ah plus 16h squared minus 16a squared all over h. Now, when we combine like terms here, what's going to happen? Yeah, the a squared terms are going to cancel, right? We have a 16a squared minus 16a squared. Those terms go away. And now if I want to simplify what I'm left with, what would I want to do next? Okay, we need to cancel out the h, right? So to do that, I'm actually going to factor it out in the numerator. So I have h times 32a plus 16h all over h. And now that h in the numerator and denominator, common factor cancels out. And we're left with just 32a plus 16h. And that would be our average rate of change from a to a plus h now. Any questions about the steps for that one? And you might be asking, why would you ever want to do this, right? What's the purpose of using a and a plus h? Well, what we've done now is we've created a generalized formula for the average rate of change of this function for any two t values that I want. And so now I could say, well, let's let the first t value be 5 and the second t value be 9. Well, now I know that my a value is 5. My h value then has to be 4 because 5 plus 4 would be 9. And then I can just plug those values into this formula and find my average rate of change. And I wouldn't have to find it over and over and over again for multiple values of t, right? I could just pick any two values I want and plug into this formula instead. So we'll stop there for today. I don't have time to start a new problem. So we'll finish up 2.4 on Wednesday. I will make the homework due on Wednesday night because I think at this point you should still be able to do all of 2.4. There's really only one other example I want to show you just because there's like a kind of a shortcut to certain types of problems. But otherwise, go ahead and be working on that. Send me those questions as you have them. Have a great afternoon, and I will see you all on Wednesday.